Okay, if folks can take their seats. It's a real pleasure for me to welcome Jamie Bach from Caltech to the CFA, and in particular as our featured speaker at today's CFA colloquium. Jamie got his bachelor's degree at Duke University in 1987 and then moved on to the University of California, Berkeley, where he worked with Andrew Lang on cryogenic sounding rocket experiments with a focus on studying high-latitude C+ emission. I think I surmised, Jamie, that activity sparked in you a real interest in detector technology, because Jamie then became one of the pioneers in developing a very novel type of bolometer. For those of you in the know, spiderweb bolometers were developed at the University of California, Berkeley, and Jamie carried that interest and expertise with him to JPL, where the bolometers were further developed and provided for such missions as the Planck mission, the Herschel mission, and a balloon-borne experiment called Boomerang, a CMB experiment. Jamie is currently working very closely with a number of us at the CFA, the details of which in part Jamie will discuss, but in particular for those of you who were able to attend today's ITC lunch, you heard about Jamie's very productive collaboration with John Kovac in developing cryogenic bolometers and telescope systems designed to provide very sensitive measurements of B-mode polarization, hopefully in time will be detected due to inflationary sources. Jamie is also heavily involved in rocket experiments designed to study the diffuse infrared background through near-infrared continuum measurements, as well as C+ line mapping. Today, Jamie will talk about what he's doing when he's not involved in these other activities, namely working on a potential MIDEX experiment termed SPHEREx, in collaboration with a number of us here at the CFA. And I'll turn it over to you, Jamie. Thank you.
Thank you, Gary, for the nice introduction. I generally prefer to talk about results, not things that might happen in the future, but today I'm breaking precedent to talk about our concept for a NASA Explorer mission called SPHEREx. And I should say the reason I'm here today at CFA is because we had our second open workshop to the community to gather ideas of what the community could do with SPHEREx. SPHEREx is an all-sky survey. It's very powerful, and there are many things you can do with it. And I just wanted to acknowledge people here at CFA who are working on SPHEREx, which include Gary, of course, but also Karen Oberg, Matt Ashby, Volker Tolles. And we still have some remnants of our meeting here. Casey Lease might also be here as well. He's one of our collaborators. Okay, so let me tell you about SPHEREx. So SPHEREx will do has three fundamental investigations, and we wanted to somehow illustrate these investigations and put them on the surface of a sphere. So that is the logo you see here. This is inflation. We're probing the early universe. This is the epoch of reionization, and then this is large-scale structure, and this is to represent the ice theme. Anyways, first of all, here's our science team, and as I mentioned, many of our collaborators are here at CFA, especially focusing on the interstellar ices theme in the SPHEREx survey. Okay, so we humbly asked the question when we were designing SPHEREx, what are the most important questions in astrophysics? And we didn't just make up our own list, although we kind of did. We also followed what's in the NASA roadmap. And so our questions are, how did the universe begin? How did galaxies begin? And what are the conditions for life outside the solar system? And actually, our mission is designed to address each of these three questions. And what I think well, I hope you'll find are powerful and compelling ways. A little bit of word about what an Explorer mission is, for those of you who don't know. Explorer missions are cost-capped, resource-capped mission opportunities that NASA sponsors. They come in different sizes, most particularly the small class. I'll tell you a little bit more about that, and the medium class. And small Explorers are around about $125 million project. Launch comes on top of that, and medium Explorers are about $250 million. And many of these missions may be familiar. They've had a very powerful influence on astrophysics, and many remarkable successes, such as, well, you can pick your favorite one. So this is the target we're going for. We have been through this once already. Previously, there was an opportunity for a small Explorer class, and then this process is done in multiple phases. So we were selected among, I think, 13 proposals to do a study. NASA funds you for a study which lasts about, in this case, more than a year. It's competitive, and indeed what I'm telling you about now is also in a competitive study, so bear that in mind. So SPHEREx and then 2 X-ray polarization missions. And the end, unfortunately, was that we were not selected. A mission called IXPI, X-ray polarization mission, was selected. However, we did a remarkable thing for those who follow NASA, which is we reduced our risk rating from medium to low in that process, which was, I think we're the only one in recent history to do that. In the midst of this process going on, there was actually the opportunity for the MIDEX proposal. So somehow we got this proposal together in the midst of the step 2 selection process. And we were again selected back in August. The 2 competing missions are FINESSE, which is an exoplanet spectroscopy mission. However, there is a European mission called Ariel, which is a medium class mission, currently in the selection process. If that mission is selected, FINESSE will drop out of the selection, and the US will contribute hardware to Ariel. And then ARCUS, which is an X-ray spectroscopy mission. And the schedule for selection is January in 2019. So within a year, we should know what's going forward. All right, so I'll first talk a little bit about the engineering. I like building instruments, so I can't resist. And for consistency, I'm going to show the small Explorer configuration. That means that all the slides I show will be consistently wrong, but at least they'll be consistent. There are changes for the medium Explorer configuration, but this is still a work in progress. So I'm just going to show the SMEX configuration, and if you have some questions, maybe I can answer them about the MIDEX. So the basic idea here is to build an all-sky spectral survey, but do it in the simplest, cheapest, most robust manner we can think of. So the basic idea here with SPHEREx is a wide field telescope. And the telescope itself is not very big. The effective aperture of this telescope is only 20 centimeters, but it has an enormous field of view, so it collects an enormous amount of light, or A omega product. This kind of approach, by the way, was sort of the same idea as the bicep-Keck CMB polarization experiments. So the field of view of this telescope is about, in the SMEX case, it's 7.5 by 3.5 degrees. Okay, so a huge amount of collecting throughput, which is appropriate if you're going to go off and map the entire sky spectrally. Now, we're in the infrared here. That's key. And so the telescope has to be cooled. And it simply cools passively. In other words, we're in low Earth orbit. The Earth is underneath us. The sun is over here lighting up the solar panels. And we radiate heat out in stages out to cold space. These are what are called V-groove radiators. They basically bounce thermal photons out to space. However, because we're in low Earth orbit, we cannot have the Earth or Sun shine on the cold parts of the instrument. So we have these deployed shields, we call them photon shields, that protect the cold instrument from warm sources, and then the emission from the instrument has to bounce out between these shields. The focus of the telescope goes to a dichroic filter, and then there's two arrays down here and two arrays here, and I'll tell you about how we do spectroscopy in a minute. Okay, this is just basically describing the thermal system. It's borrowing the approach that was used on the Planck spacecraft. So Planck is a CMB mission, near and dear to my heart, and it was at L2, but it's using this three-stage V-groove radiator. But because the sun is always behind here, it doesn't need these shield extensions, so light just radiates out to space directly. Actually, when I started this project, I wasn't sure how cold we could get in low Earth orbit, and the coldest thing in the instrument are the longest wavelength detectors. We want to cool them below 55 degrees Kelvin. And it was brought to my attention that actually a mission called COBE, also an explorer, by the way, after its cryogens ran out, it was not designed to cool this way, the detectors ran at 45 degrees Kelvin. So unwittingly, this low temperature has actually been achieved in low Earth orbit. Okay, this is just a picture of what those deployed photon shields look like. This is actually a scale model we built at JPL. It's obviously very slowed down, this movie, but you can see here these are basically just aluminized Kapton membranes, and there's three shields, and these rods are basically sprung rods which provide the force to deploy it. There's just a single burn wire that initiates this process, and then when this thing fully deploys and settles down, all of this is, the whole time of this movie is about 1.5 seconds. So things haven't quite settled down, but you can see the three shields. So we have done a fair amount of development now to get this concept ready and working. Here's what the telescope does. It's a three-mirror design. It's an off-axis thing here. As I mentioned, the output of the telescope is split by dichroic into two focal surfaces. And we paved these focal surfaces with detectors, a long wavelength detector transmitted and a short wave down here. Actually have built a prototype of the telescope. The mirror here is actually what's called a freeform mirror, which means it's like a surface of a potato chip. It doesn't have an axis of symmetry. And we're able to show that this process works well. Now, one thing is for a mapping mission, we want to have, we need to tile the sky, and there's a trade-off between how fine we make the pixels and how sensitive we are. So we've chosen a pixel scale of 6.2 arc seconds. And there's an important point here. That pixel scale is kind of large, but there's an enormous amount of information in every exposure. Because of the large field of the telescope, we see something of like 8,000 stars with known positions in every exposure. So every exposure, we're going to know exactly where we're pointed, and we can reconstruct the PSF, including sources of whatever happens, pointing jitter, what have you, from these stars. And in fact, we can reconstruct the PSF subpixel. That's our plan. So using this prior information, we have a lot of knowledge on the sky. And the way we do our science, our core science at least, is that it's all based on known positions. And so we can optimally calculate the flux of a known point source from this information very well. The way we do spectroscopy is somewhat novel. The idea here is that in order to do spectroscopy, rather than have any moving parts or a spectrometer that would rival the size of the instrument, the telescope, what we do is we simply put interference filters on top of the detector arrays. And the passband of the interference filter just varies continuously over the detector array. Turns out this is a very mature technology. It's been used in space on planetary missions, and in particular, an instrument called RALPH here, which was on New Horizons that went out to Pluto, used this approach. And there's another one called SPHEREx, also a planetary mission. Okay, so on the sky, the arrays have this pattern where you have a bandpass and it just varies continuously over the array. We have these two arrays side by side in reflection off the dichroic, and these two in transmission. So to get the spectrum of a source, we simply take exposures where we move the source in a series of exposures over the detector array. And at the end, a complete spectrum of a source would have 96 measurements taken with 48 of these pictures. Also, because this is a spectrometer, the spectral bandwidth is narrow. So you have to sit and integrate in order to get down to the photon noise limit set by the backgrounds from space. It's pretty low. So therefore, we want to sit there and integrate for a while. Turns out that is about 150 seconds, and then move to the next exposure. And while we're doing this, we're going around the Earth in our orbit. And I'll illustrate how that happens here in a minute. Note the wavelength coverage goes from 0.75 microns, that's our shortest band, out to 5 microns. Sorry, this is a little bit dated. So now it goes out to 5 microns. And at the longest wavelength, the resolution increases from 40, which is set by our cosmology theme, up to 135, as it turns out, to do this ice science. But this approach is very simple. There's nothing in the instrument that moves as a result. The only thing we need to do to get our data is just have the spacecraft point. I've defined a figure of merit here called mapping speed. This is the amount of time it takes the 1 over the amount of time it takes to map the entire sky down to a line flux sensitivity of, in this case, 10 to the minus 18. And here's the red curve is what you see is the mapping speed for SPHEREx and ground-based missions and Euclid. Out here in the optical, these ground-based surveys are generally have more speed, and as does Euclid. But SPHEREx is niche here, especially in the longer wavelengths in the infrared. It does very, very well. Now, the other thing here is I could take all of my pixels and observe just a single wavelength, and I would have a really good mapping speed at that one wavelength. But of course, I want to cover a spectral region. And so the integral of all those speeds is something called, I call the power. And so this is the spectral survey power of SPHEREx versus other things. And the whole point here is that SPHEREx is designed to have lots of power, which is what you need to map the whole sky efficiently. That's the approach we're going for here. And so despite having a small telescope, it does have a huge observing power. Okay, so this shows basically how we observe the sky. If we want to observe the spectrum of a given object here, we take this series of exposures. Every one of these exposures is taken at a slightly different place, so we observe that object at different wavelengths. And through a series of 48 pointings, eventually we get a complete spectrum. This is just showing the short wavelength band coverage. And then, while we're doing this object, we're getting spectral information over here, but incomplete. And while we're doing this object, we're getting spectral information over here as well. When we were doing this over the entire sky, we would like to just take small steps all the time, but the Earth gets in our way. So eventually, we have to do a large slew to advance the telescope so that we continue to avoid the Earth. So the way this all works out is we have a series of small exposures, and then we have to do a large one, then do this process over here, and then another large exposure, and so forth. And over multiple orbits, we fill in the celestial sphere. And after 6 months, we get a complete spectral map of the entire sky. This little movie illustrates how we observe in more detail. Okay, so we are in low Earth orbit. There's SPHEREx, that's not to scale. And we have to maintain about a 35-degree cone to stay away from the Earth, and we can't have the sun come in. So we get this region of visibility at any instant in time. And then as we go around the Earth, that region of visibility moves, and we have to occasionally do large slews. So here you see a series of these small steps until we hit the edge of that region of visibility. And then we have to do a large scan, advance the satellite. And then over the course of 6 months, all these observations will eventually tile the entire sky. We are basically observing 90 degrees from the sun all this time. And therefore, there's two regions up here at the poles that we have very deep coverage on. We observe them every orbit, in fact. So the coverage over the whole sky is shallow, basically one spectral channel every 6 months. But then in these deep regions, we have something like 60 times the coverage. And we can do unique science at the poles. Right, and at the end of 4 surveys, there's 4 trillion spectral spatial samples. So it's a fair size data set. Okay, let's do our 3 core science themes. This is basically what was driving the design of the instrument, but there's a lot more because of this all-sky spectral survey that can be done. So our first question, how did the universe begin? Well, modern cosmology posits that 10 millionths of a billionth of a billionth of a billionth of a second after the Big Bang, thereabouts, the universe went through a rapid exponential expansion. And that blew up quantum fluctuations to the size of galaxies and clusters of galaxies. Now, our best experimental probe of the early universe to date has been the microwave background. But there also can the structure of a large-scale structure traced out by dark matter and galaxies is also a cosmological probe. That's this stuff. So what SPHEREx is going to do is study the large-scale structure. And in particular, there's a signature from inflation that's best probed by large-scale structure and not the microwave background, called non-Gaussianity. It has to do with the physics that's driving inflation. And it's a different observable channel than the production of gravitational waves from tensor modes that can be studied from the polarization of the microwave background. So yeah, I'm a CMBer by training. And this is a really beautiful map from Planck that shows the anisotropies of the background. Of course, to first order, the sky is incredibly uniform. To 10 parts per million, that's a prediction of inflation. Well, a rationale for coming up with inflation, perhaps. But there have been further tests from this map. The fact that the universe is now, we can measure the geometry of the universe from the first acoustic peak in the microwave background. The fact that you see large-scale structures here that are larger than the classical horizon is a prediction of inflation. In fact, there's an anti-correlation between polarization and temperature on these super-horizon scales. It must have been set up by something. It couldn't be done with a non-inflationary type of model because it would violate causality. The spectrum of fluctuations is very nearly scale invariant as predicted, but has a slight departure from scale invariance as predicted. And the phase of the fluctuation. So this is really a nice confirmation that something like inflation happened. And the fluctuations, by the way, have very nearly Gaussian statistics. So if you want to probe inflation, we have to look for departures from the standard model here. And there are 3 ways that I know to do. I mean, there's probably more, but the first is to look for this B-mode polarization pattern in the CMB from inflationary gravitational waves. We talked about that at lunch. One can measure the primordial spectrum of fluctuations, and you can do this with the CMB and in combination with large-scale structure. And finally, the measure of non-Gaussianity. That's sensitive to the properties of the inflaton field, whether it's described by a single field model or a multi-field model. And actually, this non-Gaussianity test is complementary to the CMB polarization measurement. And so this here is showing an illustration of a very dramatic change in non-Gaussianity, parameterized in this case by a number called FNL. It's not the only kind of non-Gaussianity, but it's the most common. you can see that these changes in large-scale structure from, a change in FNL induces a change in large-scale structure. And the best way to probe this is actually to look on the largest spatial scales. Now, I should say our constraints from inflation on FNL currently come from the microwave background. This is a current constraint of less than 10.8. But an important point here is that when we observe the microwave background, we're observing a two-dimensional surface. So there's only a certain number of independent cosmological modes in that surface. However, if we're studying large-scale structure, we're looking in 3 dimensions. And so the number of accessible modes is much larger. And so for certain kinds of measurements, you can do a better job. The microwave background determinations of non-Gaussianity are getting very close now to cosmic limits. But through large-scale structure, we can improve that situation. Non-Gaussianity, models that produce non-Gaussianity as a rule are inflation models that have multiple fields. The simple kind of single field slow roll inflation predicts negligible levels of non-Gaussianity, but these multi-field models typically predict a number greater than 1. So if we want to push down uncertainty on non-Gaussianity from 10 to lower, how good can we do? Well, it also turns out that the signature of non-Gaussianity it's really twofold. One is on large scales, there's an enhancement or change in the power on large scales, but there's also a modulation of fine scale structure by that larger variation. It's because of the interaction of the fields. And as it turns out, there's 2 ways to test that from large scale structure called the power spectrum, which would access these large modes, and then this mixing through a higher order statistic called the bispectrum. So SPHEREx, what we'll do with SPHEREx is make a large all-sky 3D galaxy survey in large-scale structure. And the way we do this is we take a spectrum of everything on the sky. We take galaxies with known positions and generate their spectrum. And we've gone through a very thorough exercise of understanding how well we can measure redshifts of galaxies. So Peter Kapak, in particular, has thoroughly mocked up this process for us. So you can see here there's information coming from particularly continuum features. We're at a spectral resolution here of about 40. The higher resolution bands aren't actually showed, but they're higher, 135. Most of the redshift information for most of the sources are coming from continuum break features, or this 1.6 micron bump, and then there's a redshifted 4,000 angstrom break. That's carrying most of the information, but there are also lines that give us redshifts. And we've simulated this whole process by taking real data from a deep survey called Cosmos, much deeper than SPHEREx will ever go, injecting these sources into simulated SPHEREx observations, calculating the spectrum of the sources we see and fitting the redshifts, and then comparing it to reality, because this survey, we know all the redshifts of what we're putting in. And so this process works extremely well, and we can take individual galaxies and characterize not only their redshift, but also their type and the error on the redshift. So the end result here is SPHEREx is very good at getting redshifts, especially at the lower redshifts, which is an area that is complementary to missions like Euclid and WFIRST. So here what you see is the density of sources with redshifts as a function of how accurate their redshifts are. So the most accurate redshifts here, 0.3%, those are generally the bright sources at low redshifts, but as we allow for larger errors, we have more galaxies, and this the number goes up quite a bit, extends out to higher redshifts, and we hit what's called the cosmic variance limit, hitting cosmological noise. Basically, you can see where we hit as a function of the accuracy, but For the low accuracy ones, we're at to a redshift 2. For the high accuracy ones, it's somewhere below 1. And these two surveys allow us to carry out these two tests of non-Gaussianity. The inaccurate sources are good for the power spectrum, where we can access the large spatial scales. We need a lot of galaxies, but we don't need great redshift accuracy. And then this bispectrum test, we use the most precise sources. And these two measurements are very, very different and independent, and we can check them for consistency. One thing I should say is that the signature of non-Gaussianity is really on the largest scales. And so going out into the infrared is important. One of the biggest systematics we worry about is just attenuation within our galaxy. That gets a lot easier if you're out in the infrared, where galactic extinction is lower. But we still have to correct for it. And we also need to characterize our noise on large spatial scales. Again, being in space, that's something we can do extremely well. So for the SPHEREx study, what you see here is on the y-axis is the running of the spectral index. That's a metric from inflation, an observable, and primordial non-Gaussianity. Our current errors are given by this very large blue ellipse, mostly coming from the microwave background. SPHEREx will make a dramatic improvement here. With the power spectrum, we get to this yellow ellipse, the bispectrum, this green orange ellipse, and then the combination is that little red place. The target accuracy on FNL allows us to just distinguish between multi-field models here, which typically have FNL more than 1, versus single field models, which would predict FNL much less than 1. You can also see SPHEREx does a pretty good job on other cosmological parameters, including the spectral index itself and the running of the spectral index. So it's pretty powerful, but it's also nicely complementary in terms of its redshift coverage to Euclid. Okay, let's move on to our second theme, studying the history of galaxy formation. And this is the same figure, basically, but now I'm filling in what happens here at later times. After the microwave background, the universe goes through a period of dark ages until the first stars and galaxies turn on and ionize the surrounding neutral hydrogen. Out to at least a redshift of 6, the universe is highly ionized, and galaxy formation peaks, cosmic noon, if you like, about 5 billion years after the Big Bang, and has been on a gradual decline today. Now, one can study the history of galaxy formation by studying the individual galaxies themselves, but there's another way to do this, which is to look at the background itself. And the background encodes all sources of emission from the peak of star formation, but there also has to be components from this first period from first galaxies. Now, the problem with studying the background has been the foregrounds, if one does absolute photometry. So this is a view of the sky just after sunset. So here's the galaxy. That's one foreground. But this foreground is perhaps more pernicious. This is the zodiacal light. It's the scattered sunlight from dust in our solar system, from interplanetary dust. And it's very bright, especially in the infrared. So rather than do it that way, what SPHEREx does is it actually will look at the distribution, essentially doing an anisotropy type of measurement, and get at the extragalactic background that way. On large scales, where galaxy clustering is linear, it turns out that galaxy clustering is a great tracer of dark matter, and the light you see is basically proportional to the brightness of the clustering that you see. It's basically a tracer of the total light emission. Now, you can also get more information by studying the properties of a map on finer spatial scales. But in terms of total background, this large scale with linear clustering is what we use. And so This provides an independent means to assess the total light production through cosmic time. So if I took a classical survey with a large telescope, I could tag these individual galaxies, determine their redshift, and map out the production of galaxy populations over cosmic time, and I'd be limited to how faint a source I could see. The SPHEREx way of doing this measurement is we have a small telescope, so that's completely hopeless, but we study the structure itself. We don't look at the individual sources. We look at the amplitude of the large-scale pattern at many wavelengths. The advantage of this approach is that we're sensitive to all components of emission. So diffuse components, dwarf populations that would be too faint to be seen by a large telescope, those all democratically contribute to the total background, which we measure. We don't care about whether the source is diffuse or compact. So, and these kinds of emission, for example, we know are actually important. At later times, if you look at galaxies today, many of them have very extended tidal tails, and adding up the light from those stars that are in stripped tidal tails, it's a non-negligible contributor to the total background light. But that's an example of a kind of emission today that we'll see very nicely with SPHEREx. At early times, the first galaxies, current thinking is that dwarf galaxies are the dominant light from those. They're going to be faint and hard to detect at the highest redshifts, even with JWST. But again, we'll see the integrated light from those first stars and galaxies democratically. So very independent from and different from the galaxy counting approach, and hopefully we can put these two pictures together and get a consistent story. This kind of measurement has been done in the far infrared. So here's an illustration with Herschel, which is a 3.5 meter far infrared telescope in space. The confusion limit's a serious issue, even at 3.5 meters. So this is a simulation here showing what a Herschel map looks like with all the sources in it. And then these are the sources that one can actually just extract and say, that's almost certainly a single object there. Where we have all this blending, it's hard to pull out the individual sources. So, this in the Herschel case, this would be the point source method, but then we can use all the information in the map in the power spectral method. This is actual real Herschel data, by the way, and Herschel was very from the SPIRE instrument, and Herschel's very capable in terms of mapping a lot of sky. So this region of sky, you can see the size here. It's enormous. You see a couple of lens galaxies, by the way, but your eye just picks out immediately this large-scale clustering from the map itself. And so here's data from that map, and I mean, it's really beautiful. This is a power spectrum, and at these large scales, this is the clustering signal. The different cuts here are cutting out detected sources as we march down in flux. So as we march down, you can see that this clustering signal is coming down a little bit, but most of this amplitude is coming from all those sources, all the emission from the sources we can't see individually. Now, in the far infrared, the problem is that we see a galaxy has almost the same spectrum as observed, or brightness as observed, independent of redshift. And therefore, it's difficult to know the redshift history. You know the total emission, but then untangling the redshift history, you need spectral information. And so the ambiguity here is what's the history, and this method is not as good for that. But in the near infrared, we can have more wavelength coverage and break that. Here are some results in the near infrared. These kinds of measurements were done with Spitzer by a couple of groups, and with a rocket experiment called CYBER. And there's an interesting signal. This is the total clustering signal as a function of wavelength, and it appears to be pretty bright. And the exact origin of the signal is something of a mystery, whether it arises from late times from stripped stars or is a component at high redshift, which would have to be very bright. And the key to distinguishing these scenarios is to make multi-wavelength measurements. So SPHEREx will have enormous power and many wavelengths to disentangle the components of the extragalactic background. Here's the total signal, again, fit as a model through these data points, and the SPHEREx points here shown at 100 sigma. So the total background will be measured with exquisite precision, but there's enough statistical sensitivity to search for an epoch of reionization signal in the total. And that's because there's an enormous amount of spectral information. In this case, we've binned the spectrum into broad channels, but not only do we see the electromagnetic spectrum, we see all the cross spectra between all the maps. And each of those maps has is sensitive to a different history. So there's a huge amount of information in all those cross spectra to disentangle the history. SPHEREx can also do this in line mapping. There's an emerging field called intensity mapping, which is to do this in emission lines. And what's shown here is the sensitivity that SPHEREx would have in H alpha, O3, H beta at low redshifts versus the total brightness expected. So SPHEREx has the sensitivity to map out H alpha emission, all the way from the present day out to a redshift of 6. And then Lyman alpha from epoch of reionization is much more uncertain, but there are meaningful measurements to be made out here, and a crossover between H alpha and Lyman alpha at redshifts between 5 and 6. And then for our third theme, what are the conditions for life outside the solar system? So the history of our own solar system is that the water on Earth appeared to have an interstellar origin. It came from interstellar ices that came into the inner solar system at some point, perhaps in the late bombardment. There's a debate about how this actually took place, whether the water came from the Oort cloud or from the Kuiper belt, and Gary can tell you a lot more about it. But undoubtedly, water's had a big impact on the habitability of Earth. And it's not just water ice. Interstellar ices have other materials such as carbon monoxide, carbon dioxide, methanol. These are organics, and could also play a big role in the formation of life in early phases of star formation. So if you want to understand the question about suitability for life outside the solar system, you have to follow the water. And in clouds where young stars are forming, 99 or more than 99%, more than probably 99.9% of the water is actually not in the form of water vapor, it's in the form of water ice. Okay, and as it turns out, these ice features show up here in the near infrared. There's not only water, this very broad feature out around 3 microns, there are narrower features from carbon dioxide, carbon monoxide, and methanol. And these ice features have been studied, but not surveyed. So that's the role of SPHEREx. SPHEREx is going to make a survey of the abundance of interstellar ices, understand how they're formed in the interstellar medium by looking at absorption in dense molecular clouds that are the hosts for forming star systems by seeing absorption to a background star. We'd see these ice features in absorption. And then we can look at the processing of ices throughout the early phases of star formation, in the envelopes of forming stars and in disks, and even in some systems going through violent events analogous to the late bombardment. Again, we've modeled this extensively, and the question is how big of a survey can we do? There's something like a couple of hundred of these ice spectra that have been made to date through space measurements. And so Gary carried out a study to calculate from WISE data, this is infrared data at 3.4 and 4.6 microns, to see how many sources we could detect. And our standards are pretty high. We want to be able to see these sources at 100 sigma per channel and have them be well isolated and embedded. And it turns out there should be easily over 1 million of them detected according to this criteria. Our requirement's quite low, 20,000. We think that would be fantastic, but I think we would all be surprised if that number was less than 1 million. So this is going to be a game changer in terms of the study of ices. We'll see the evolution and properties of ice in all kinds of different environments. And then finally, SPHEREx will map the spectrum of the entire sky. So every 6 arcsecond pixel in the sky will have a spectrum. In fact, it'll have 4 spectra because we'll observe for 4 surveys. And the total data set here is really, really powerful. They're going to be spectra of many galaxies. Anything you can do with statistics, by the way, there's so many objects here that's got a lot of potential. Spectra of stars, including dust-forming star, low-mass stars, and target stars for exoplanet missions. And then a host of other things. For example, we now know there are at least 2 quasars above a redshift of 7. When we initially made this view graph, it was 1 question mark. And there are probably more. And SPHEREx is these are eminently detectable in the SPHEREx data set. They show up as red objects. They'll be in the data, and they're going to be great for studying the properties of epoch of reionization when followed up. There'll be a host of asteroids and comets, and we'll get spectra for many of them. One can map emission lines over our galaxy. We're planning on serving out the data quickly, and you can see the sensitivity of SPHEREx here. Again, this is the SMEX configuration of SPHEREx, so actually the numbers are somewhat better. Typically around 19th magnitude for the whole sky survey for every spectral channel. And in the deep region, they'll be deeper. So we can get spectra for every 2-mass source with high signal to noise, and we'll have detections really of even, these are broadband measurements from WISE. We'll have measurements for every WISE source as well. Maybe not great spectra for all the faint ones, but very nice and complementary. And this kind of all-sky catalog will also be very useful. We mentioned JWST, but it's really has many synergies with other missions, which led us to the point of having this workshop. The workshop here, we had, I guess, about 50 people. And the question was, what would you do with SPHEREx? And in particular, we wanted to know, what would you do with SPHEREx combined with your favorite mission? So I had a lot of nice input. This follows on. We had a workshop like this again in 2016 in Pasadena. We wanted to be a little more geographically diverse now. And there were quite a number of ideas that came as a result of that, some of which we hadn't thought of. And we heard more. We're still processing the results of the workshop yesterday and the day before. But just to give you a couple of examples, one is missions like TESS and looking into the future, Plato, are going to look for transients around relatively bright stars. It turns out the mass and radius of the host star is one of the biggest uncertainties in understanding the properties of the exoplanet that's detected. So SPHEREx will just do this as a matter of mapping the sky, get spectra to better nail down the properties. And there's a synergy here using SPHEREx together with Gaia to help nail that down. All sky X-ray surveys have a great synergy with SPHEREx as well, both for clusters like this. SPHEREx can get the redshifts and also look at other interesting things about the clusters, like evolution of the galaxy populations with environment. But also, as I learned, stars. There are many sources in these X-ray surveys from protostars. And again, we'll have spectra for all those that may have some influence on the environment for the formation of ices. So lots and lots of ideas. We're open to whatever new, we're always open to new ideas. And if you have input, we'd certainly love to hear it. We wrote up the results of this 2016 workshop from Pasadena, and planning to do the same thing here for the 2018 workshop. There's also a white paper from 2014 just describing the overall science case that you can look up. So, thanks for your attention.
Great. Any questions? Edward?
In your list of ices that you're going to be looking for, I noticed you don't include hydrogen. And yet, doesn't hydrogen ice with the triple point well above the present temperature of the universe, shouldn't that be the dominant carrier of the dark baryons?
Do you want to take that one?
I'm unaware of any ice feature in the SPHEREx band.
Yes, I'm unaware of any either. And so, on the other hand, what if most of the water in the universe is tied up in ices? Sorry, not water, most of the hydrogen, the missing hydrogen, is tied up in ice. Okay, well, I guess your experiment doesn't do it.
Yeah, we can't attack that. I don't know what the sublimation temperature of a pure hydrogen ice would be, but I would imagine it would be quite low.
The triple point is 13.8 Kelvin, and that's well above the 2.7 degrees background temperature.
But not so far above the temperature of most dust grains. And so, well, at any rate, I mean, we can debate this, but it's not a topic that SPHEREx can weigh in on.
Okay, thank you.
Yep.
So, simple question actually. In your ice spectra, you showed a fairly prominent feature for XCN.
Right.
What's X?
Anything. It's a CN stretch mode attached to a different
So
molecule.
CN attached, is
Yeah.
it primarily HCN or?
It can be primarily HCN, but as Jamie just said, it's a prominent feature of just the C and the N long.
So what changed when you went from the SPHEREx to the MIDEX?
Right. Well, I can't tell you everything, but we've improved the field of view to get somewhat more sensitivity. And another important thing is with the SPHEREx proposal, we were struggling to serve out all the data in a way that the community would expect it to be served out. But that's something we can now do quite well with more money that's in the MIDEX.
It did not enlarge the telescope aperture,
Did not enlarge the telescope aperture.
which is kind of a surprise. Okay.
We thought about it.
Well, I'm sure you did. It's just a surprise.
That is to say, it wasn't one of these things that we didn't think might help, but we looked at the pluses and minuses of it and decided, maybe counterintuitively to you, that actually, you know, the A omega argument favored, and other arguments. You know, there's another dimension to getting a mission selected, which is low risk and low cost. And the 20 centimeter telescope, in addition to being scientifically viable, was initially given a low risk rating. So you don't undertake changes to a low risk rating without really good reason.
I will say that you can gain sensitivity faster by increasing the field of view and the aperture. That's also perhaps counterintuitive.
Yeah, that is definitely for me.
Yes,
So how much did the cost go up?
Well, the cost cap went up by a factor of 2.
A judicious team will maintain healthy reserves.
So
So you're actually going to repoint the entire instrument in little stuttering steps, or just move them slowly from?
no, it has to be pointed during the integration. So the spacecraft is designed to be agile to do this, and so it slews and then has to maintain pointing during the integration, which is about 150 seconds. It has, you saw here the star trackers,
Yeah.
but they can be used for pointing the slews. Didn't
What limits the 2-year lifetime? Or it sounded like it was 2-year lifetime. Of the
That's right. Nothing. There's no consumable.
So, right. So you could, if the money was there, do more service.
Right.
So a couple of things. You will be selected in 2019, assuming that happens. So the overlap with observing for JWST and giving things to point to JWST at is going to be pretty small.
It's going to, well, a lot
For
of
the
it-
nominal lifetime.
On the nominal lifetime, it will be very tight, but it's expected that JWST will
Right.
go beyond its 5-year
So,
lifetime.
as a science question, you showed your sensitivity in each of the many bands, but there are cases where you'd like to co-add the bands
Sure,
next to each other, particularly looking for very high redshift quasars.
sure.
We want the lowest limit on the non-detection.
Yeah, that's right, and the first order goes as a square root of the number of bands of code.
So you can do it quite well.
Going back to your FNL figure of merit, what's the lowest number that you can expect to reasonably detect at 2 sigma? Or alternatively, if FNL is 0, what's the upper limit that you hope to propose?
Well, as I said, our requirement is FNL of 1 2 sigma.
Is it local?
That's, yeah, look.
Any other questions? Yes, sir.
What are the prospects, if any, for learning something fundamental about the properties of ices, water ices, at low temperatures?
What would you regard as fundamental?
Sorry?
What would you regard as fundamental?
Well, some properties that we don't know about from the laboratory here. Maybe there's nothing.
No, I think this is where the complementarity between SPHEREx and JWST comes in. JWST will cover the same wavelengths and therefore the same ice features and more. It goes beyond 5 microns, and obviously with its larger aperture and higher spectral resolving power spectrometers, it will drill deep, but not wide. So JWST may collect several hundred ice spectra. There'll be very high quality, very high spectral resolution, but we will get everything, and we will be able to look at evolutionary changes that will be difficult for JWST by observing basically every available line of sight in the Milky Way. We can see how the relative abundances of these ices change from diffuse clouds to dense clouds to young stellar objects to disks, and we'll do it in hundreds of thousands and most likely millions of lines of sight, where JWST will come in, hopefully, with an overlap of the missions. Any line of sight where the ice content is particularly interesting, we can work with JWST to make sure that we get higher spectral resolving power spectra of those ices. And so, I mean, that's sort of the interplay between the two missions. One advantage that JWST will have is with the higher spectral resolving power, you can map out the actual profile of the ice features quite well. And from laboratory experiments, some of which Karen Oberg here has done, you can begin to tease out how much ammonia is intermixed with water and how much CO2 is intermixed with water. It slightly changes the profile of the ice feature. And you can perhaps tell if the ices are intermixed with each other in an amorphous way or whether they're layered. And there are various arguments as to how the ice gets laid on the grains. That there are different scenarios that produce either this amorphous or layered structure. So that will be the domain of JWST, but in having millions of lines of sight, we can tackle things they can't, the evolution and the interesting lines of sight. I don't know if that answered your
Yes,
question.
it does. Thank you.
Yes.
So I'm surprised you didn't mention overlaps with LSST.
Right.
If you did, I've just missed it. Because doing this full sky survey, you're going to be able to provide infrared counterparts to LSST transients seen in the blue that are
Yeah,
in fact,
so
high redshift objects.
there are, of
That
course,
opens up a huge
There are, of course, synergies with LSST. For transients, transients are the one thing that we don't do particularly well because of the coverage, unless you're lucky and it's in a coverage region. But we can certainly provide the spectrum of what was there before.
Exactly.
That happened.
I was talking to Gary about that in another context, but I think that's a very interesting advantage of the survey.
So what are your odds of being selected?
I'd like to say 1 out of 3, but you never know. I mean, stuff happens at NASA, right? JWST is launched.
Erwin, just coming back to your question, I would also mention that one of the early release science programs on JWST is dedicated to the study of ISIS, and it will look at a 2x2 arc minute region of the sky. So it gives you a sense of, what is a significant project and the aerial coverage for JWST versus covering hundreds of square degrees. Okay, well, if there are no other questions, let's thank Jamie again.